Okay, hi everyone. So is there any question?
Yeah,
Question?
hi, Professor.
Hi.
I have a question.
Okay, sure.
Can you explain more about the slide deck? I mean, what we should. I don't know the meaning of a slide deck.
Slide deck means just a series of slides. So a page in the slides that you have is just one slide. If you have multiple slides back to back, it's a slide deck.
You mean a PowerPoint? We can use PowerPoint too.
Yeah. So the reason that I don't call it PowerPoint because some people might use other software to generate a slide deck. PowerPoint is not the only software for that. Someone might use LaTeX for that. Someone might use Google Slides, or someone might use PowerPoint. PowerPoint is just one of the softwares. Yes.
Thank you so much.
No problem. So yeah, just briefly, as I said before recording, please your presentation. Yeah, I think that would be best if you introduce your problem, then define your problem mathematically using an optimization problem. So minimize or maximize the cost subject to the constraints. You might have multiple optimization problems, that's fine. And then the optimization method that you're going to use. And then a brief introduction to that optimization method, especially if it's not already introduced in the course. But even if it's already introduced, it's a brief introduction that would be nice. And then how you use that optimization method for your optimization problem, the challenges that you faced and how you overcame them, and then the results and the discussion and analysis of the results. Please don't report the results without any analysis, because the value of results would be visible if you discuss them. Yeah. Any other question? Oh, by the way, as I said, please, I will announce the order of teams to present before the class, which is next week. But I would appreciate a lot if every team, all teams, including the team which is going to present at the end, be present in the beginning of the presentations, because I want every team to listen to other teams and learn from each other. Any other question? No? Okay, great. So let me share. Oh, by the way, so based on the calendar, so as we are going to use the next session for presentations, this is the last session for lectures. However, we have some more stuff which I think they won't fit in this session. Therefore, I will record maybe one or maybe two with different lengths, one or two lectures. I think the other one of them will be bonus lecture. And there is no exam, so just for the sake of learning, okay? And whatever remains, I will record them. I will put on YouTube, and I will share the link in course links so you can learn all the topics that we are gonna cover. We covered most of them. Just maybe some of them will not finish today, and we'll have lectures on YouTube so you can watch them later. And then please let me know if there is any ambiguity or question about them. Yeah. Okay, the reason that I put the presentations in the last session because I respect your schedule and I didn't want to that to conflict your schedule. Okay, let me share screen. Do you see the screen? Do you see that? Okay. Yep. So great. So before I go and continue the distributed optimization methods, one typo that we had, I think here I mentioned in equation 25 in the slides for second order optimization when we were talking about line search, Wolfe conditions. I said this is gradient of f. We had the same typo in RMU line search too. Sorry about that. So 25 and 26 is our gradient of f. So P transpose gradient of F here, I fixed that, but in the next slide, I didn't fix that. So I repeated them here. So these are gradient of, so P transpose gradient of F, and here also P transpose gradient of F. Here also, when we were talking about the strong curvature condition, this is also P transpose gradient of F. Yes. So that's one typo that I had, and I wanted to correct that. And by the way, this was, as we talked about, this was the Armio condition, and this was the curvature condition. Of course, Armio condition was proposed before Wolfe, so Wolfe added another condition named curvature condition to Armio condition, and they both were named after Wolfe. So if we use the first one, Armio proposed that, but Wolfe combined this with another curvature condition. That was the Wolfe conditions for line search. And here, by the way, it's usually used, although I have said it can be used for first order methods too, but it's usually used in Wolfe conditions are usually used in second order optimization, but and Armio condition or backtracking line search or the simple line search is usually used for first order optimization. Why? Because the curvature condition especially is used for making sure that the approximation of Hessian, recall here, approximation of Hessian remains positive semi-definite, especially in quasi-Newton's method, because Hessian should be positive definite by definition. Therefore, the curvature condition usually is taking care of the Hessian. That's why Wolfe condition, including the curvature condition, is usually used for second order optimization. And Armia condition only is gonna usually use for first order optimization. So that was one thing that I wanted to let you know. And then let's continue the distributed optimization. But before that, let's briefly review what ADMM was. So we started from alternating optimization, and then and before that, so we started from alternating optimization in the previous session, and then where we alternate between the variables of the optimization problem. Then we went to dual ascent method, and then to dual decomposition method, and then augmented Lagrangian method, and then we went to ADMM. So that was the development that we had toward the ADMM algorithm. And so here we said that, okay, yeah, here we said consider this optimization problem, equation 17, and then we know that we can update x1 and x2, assume that it has only x1 and x2 variables, and then know the dual variable. So we could use, according to the augmented Lagrangian method, we can use this for solving the problem, and this was the we said that this was the original ADMM, which has two optimization variables, and then we simplified that, and we came to here. So after simplification, we saw that we can have this where u is the change of variable from nu to u, and then we said that let's have a general optimization problem where we also have inequality constraints, and we might have more than two optimization variables. And then we use the trick, because as we also saw in the interior point method, usually the inequality constraints are a pain in the neck. So in the interior point method, we also brought the inequality constraints as an indicator function for a hard penalty in the cost function. And then we use the Newton's method with with equality constraints to solve that. Do you remember that? So again, here, inequality constraints are a pain in the neck. So we can convert them to equality constraints, which are easier to handle here. And then, so we converted this equation to this. And then we said, okay, let's use lambda and nu as the dual variables for the equality and inequality constraints. Lambda for inequality and nu for equality, but inequality constraints have been changed to equality constraints already. And then we wrote the augmented Lagrangian for that. And then this was the ADMM. We formed the ADMM for that. And then we simplified that again. We put it back in the Lagrangian. So the augmented Lagrangian became this. And then we had the change of variable also lambda from lambda to u lambda and from nu to u nu. And then we saw that, okay, here, this is the ADMM in general case where equations 28, 29, 20, and 30 are each several equations. So this was the ADMM in general. Now we continue ADMM by saying that how do we use ADMM for distributed optimization? Let's have a discussion on that. So ADMM is one of the most well-known algorithms for distributed optimization. And if the problem can be divided into several disjoint blocks or several primal variables, so if we have sometimes even the problem doesn't have several variables, but it is convertible to some problems which have multiple variables, and we'll see some examples. We can solve the optimization for each primal variable on a separate core or server. Therefore, it's parallelizable. For example, equation 28 for I, what was the equation 28 here? We had this, so I'm repeating it here. Consider these. So hence, we can for each of the variables, we can run them on a different core or server. And in every iteration of ADMM, the update of primal variables can be performed in parallel by distributed servers. At the end of each iteration, the updated primal variables are gathered or aggregated in a central server so that the update of dual variables is performed. Equation 29 and 30, which was here. Do you remember? So then, so these can be done in parallel, and then we should aggregate them in order to calculate the dual variables. Again, as I had mentioned in the previous session, this reminds us of federated learning. The idea of federated learning in machine learning is that if we have we can have several neural networks on different, each of which is on a server, on a different server, and the servers are disjoint. We have a central server, so we send our data to or our weights to the different servers. Their servers might have their own data, so they tune the weights based on their data, and then we aggregate them back into central server. We can take average of them and then send them back to the servers. So the servers fine-tune the weights, and then we collect them, we take the average, and we send them back to the servers. So this goes back and forth until we have convergence. This is federated learning. And as this also can be, so it can be used for different uses. So distributed algorithms can be used either for making it parallel and faster, because we don't need to have a huge data in one server. We can divide data between servers. So that's handling big data and also making it parallel and fast and more efficient. That's one use. And another use is privacy, because if servers don't see each other, they only see the central server. Of course, there are some weaknesses in this system where someone might attack the central server. So if we have an attack to the central server, this whole system fails, right? However, ignoring that, the servers don't see each other. They only see the central server. Therefore, their data is private. So that's an interesting thing. It has multiple uses. Distributed algorithms have these two use cases. And making optimization problem distributed. Now assume so the ADMM was used for distributed problems, but even if the problem is not distributed, we can make it distributed, maybe in a fake way, in order to be able to solve that optimization problem using ADMM and even solve that in a parallel way, right? So we can make it distributed, even if it's not distributed. How you see that? We can convert a non-distributed optimization problem to a distributed optimization problem to solve it using ADMM. Many recent many machine learning and signal processing papers are using this technique. If you go and see, they use it a lot. So now consider univariate optimization problem. Consider a regular non-distributed optimization problem with one optimization variable x. So now compare this equation 31, this optimization problem, to this optimization problem here or here, equation 26. Here we had m variables, right? So fi xi. However, here we have only one variable, x. Okay, now sigma I fi x, not fi xi. Okay, and we have also inequality and equality constraints. Now, this is not a distributed optimization problem. This is a general optimization problem, although the cost is decomposable here. Okay, the problem can be stated as this. We can say, okay, let's convert fix to fixi. However, so we have m xi's, so x1 to xm, m variables. However, we add constraints to say that xi equals z. So for all I from 1 to m. So it means that it's actually m constraints. It means that x1 equals m, x2 equals m, x3 equals m, and so on. So it means that when x1 equals m, x2 equals m, and x3 equals m, until, sorry, not m, I apologize. I mean x1 equals z, x2 equals z until xm equals z. It means that all x1 to xm are equal to each other. And it means that they are actually one optimization variable. So that's a good technique. We can introduce m optimization variables, but we equate them to each other. Or we equate them to one variable, and as they are all equal to one variable, they are equivalent. So we introduce m variables and use the trick. So this is a good technique that we can use in order to make our optimization problem distributed. And then, as you see, this is in the form of equation 26, simply solvable by ADMM. Okay, now let's continue. Stay here. Equation 32 is similar to equation 26 as we discussed, except that it has two m equality constraints rather than m equality constraints. Doesn't matter. The approach is the same. Hence, we can use ADMM updates similarly to equation 28, 29, and 30. Here, we had them here. So we can use them in order to solve the optimization problem with a slight change because of the additional m constraints. Doesn't matter. So here, for example, here we had m equations. We might have two m equations. Doesn't matter. We have more than m. The number of equations will change, but the approach is the same. The approach is the same. And so we introduce m new variables, m new dual variables for constraints. That's an important thing you should note, that we have added m new constraints. Therefore, we need to have m new dual variables. So, and update those dual variables as well as other variables. In other words, so we using that trick, we convert yi to yi prime, and we have lambda i's for them. We also for this one we have new i's, and for this one then we can introduce, I don't know, something else like eta i's. So we will have a set of new dual variables for the additional constraints that we introduced. And the augmented Lagrangian has some additional terms for those new constraints. How do you calculate the augmented Lagrangian? With the same approach that we had here and simplified that. So it's exactly the same. And the Lagrangian and ADMM of this are not stated here because of the similarity. This is a good technique to make a problem distributed. Use ADMM for solving it and solving it in parallel servers. And it's used a lot in the literature. So what we talked about here was the univariate optimization problem. Now assume it's multivariate. Okay, we might have M optimization variables. And now let's see what happens. I'm considering some SI as feasibility points. So I'm considering either equality or inequality constraints as some feasibility sets. So I'm writing the constraints in this way now. Now, this is a general optimization problem with M optimization variables, right? And it can be any constraint, such as belonging to a set SI. It can be equality or inequality constraint. Now, let's see what we can do. We can embed the constraint in the objective function using an indicator function. So assume phi I is the indicator function. Phi I xi is the indicator function for xi being in belonging to the set Si. So we can do that. And as you see, we are introducing a hard penalty. So as it is a hard penalty, before approximating the indicator function, these two are exactly equivalent, all right? So, and it is 0 if it's not, if it's satisfied, otherwise it's infinity. The problem can be then stated as this. Now, a good thing you should note that is that, okay, so consider this optimization problem. So we converted equation 33 to this problem, right? Now we have another step. We convert this optimization problem to this. How? We are saying that let xi here in the regularization term be zi now. So we introduce m new variables z1 to zm, but here again we're using the same technique to make the problem distributed. We say that xi equals zi. It means that x1 equals z1, x2 equals z2. So this means f1 x1 plus phi1 z1, but z1 equals x1. So we have f1 x1 plus phi1 x1. Also f2 x2 plus phi2 x2, because z2 equals x2. There is a slight change. There is the light difference from this and this. What is this? Here we are setting all x1 to xm to z. It means that all x1 until xm are equal. So x1 equals x2 equals x3 until xm. However, here x1 equals z1. x2 equals z2. It doesn't mean that x1 equals x2. No, it means that only we are introducing some new variables, but we want to say that x1, so these two are the same. x1 is z1, x2 is z2, right? X and x3 is z3. So this is the approach that we have. So we are changing one of the terms to be a function of zi rather than xi. That's a good technique. Now we have this as the constraint xi minus zi equals 0 for all I are equality constraints. So these are equality constraints, right? Each of which is an equality constraint. We can use equation 23, 24, and 25 as ADMM updates for this problem. What was 20? So I have repeated them here. I have repeated equation 23, 4, and 25 here. This was used for when we have, let's go back a bit. Do you remember? We had equation 23 to 25 for when we have only equality constraints. We started from here, then we said, we simplified that and we came here. And here also, we only have equality constraints. Here we only have equality constraints, therefore we can use these equations for solving them. And now compare equation 35 and 36, these two, with the proximal operator. Recall the proximal operator from 2 sessions ago when we were introducing proximal mapping. So here you can see that proximal operator is used with ADMM also. We'll see how. So if you compare equation 35, 36 with the proximal operator, you can see that there is a close similarity. Compare these with these. It means that actually ADMM is having a proximal mapping in itself. How? So how did we come up with these? In the previous session, we proved that. We simplified ADMM and we came up with equation 35, 36. And interestingly, they are in the format of proximal mapping. So if you compare these, you will have this. So these become simplified to these equations. For example, how do I say that? Here, I'm saying that I'm telling you how I'm coming from here to here. So for this, prox of x with the function g is argmin of u, gu plus 1/2 lambda u minus x squared L2 norm. Okay, now what do we have here? Here, rather than u, we have x. So consider u to be x in this formula, in the formula of proximal mapping. Here, I'm saying that look at this and this. Compare these two. Okay, so rather than u, we have xi, and here we have x. Here we have u. Here we have minus z plus u. It means that minus zi minus u I. Here we, rather than x, we have minus z minus u. Hence this. And the function is f rather than g. The function is f rather than g. And the variable, so the left-hand side is the same. The right-hand side is the proximal mapping. You can do the same for this. Compare this with the proximal operator to find this. So here, the variable here. The variable is z rather than u. The function is phi rather than g. And rather than x here, we have z minus, no, sorry, x minus u. Here, because the optimization, the variable is z. Therefore, the other two terms, which are, we have here u minus x. So we have z minus x plus u, right? So let me write it down because it might need some calculation. So here we have x minus z plus u. You can write it as z minus x minus u, right? Because it's a squared L2 norm, so you can multiply inside of it by -1. Doesn't matter. Then compare this with the proximal mapping. You will see that this is, you will come up with this. And we'll come up with this. Okay. Now the third equation I have repeated without any change. So this was simplified to this using proximal operators, and that's an interesting thing. Note that in many papers, such as this is one of the papers, we only have m equals 1. What do I mean here? Do you remember? Here we had summation of fi, or here we started from equation 33. We have summation of fi xi, but sometimes we only have one, so we don't have any summation. But still, we can embed the constraint in the objective function, and we also can say subject to x equals z, because we only have one variable, right? So we have only primal variables x and z in those cases. And according to the lemma, we had that the proximal, do you remember we had in the 2 sessions ago, we had the proximal operator of indicator function is projection. So as a function phi I x is an indicator function, do you remember? We were embedding the constraint into the cost function using hard penalty, and we said that phi is an indicator function. Here we also have the proximal mapping here. Here the proximal mapping where the function is phi, which is the indicator function. It means that this function is actually a projection of its variable, which is xi plus ui, onto the set Si. Why? Because phi I is indicator function for belonging to Si. Recall this equation, right? Therefore, we can simplify the second equation in this here. The second equation, which is Zi equals prox of xi plus ui by projection of xi plus ui onto the set Si. And we already talked about projection 2 sessions ago. An example, assume that the constraint is having xi to be orthogonal matrix. Actually, in 2 of my papers, I have used this. So I said, I want X to be an orthogonal matrix because in my papers, X was the optimization variable was a projection matrix, and I wanted the projection matrix to be orthogonal. Then in the ADMM, in the second thing for Z, I said, okay, it's simply saying that, meaning that I project onto the orthogonal cone, and we already talked about that 2 sessions ago, that we proved that it means that we set the singular values to 1. And then we reconstruct the singular value decomposition of the matrix by having singular values set to 1. That's an interesting thing. So in other words, if you have, for example, minimization of some function f of x, assume x is a matrix, subject to x transpose x equals I, assume x is, I don't know, any function such as x transpose a, for example, a is a known matrix. You see this format a lot. This is used in PCA, in many things. So it has a closed form solution, which is actually an eigenvalue problem for my matrix A. But I'm not going to talk about that. Still, you can solve this iteratively using the ADMM, using the same thing that I introduced here. But in the second equation will be projection onto the orthogonal matrix cone by setting the singular values to 1. That's an interesting thing. So although it has a closed form solution, you can solve it iteratively. Okay, an example of ADMM. So you know one of the use cases of ADMM in practice. I have brought it from my own paper. So I proposed a method named image structural component analysis, which is inspired by PCA, principal component analysis. But I said I want to, so principal component analysis uses mean squared error. I said, but mean squared error, if you are aware of image processing, especially image quality assessment, you know that there is some measure named structural similarity index, or SSIM. It is proposed by Professor Zhou Wang here at the University of Waterloo. It's one of the most well-known image quality assessment measures, okay? And so I said, and also Zhou Wang discusses that mean squared error is not good for calculating the image quality assessment, for assessing the quality of image. So we need to use SSIM or other measures. Why? Because if you have a distortion in your image, mean squared error does not replicate what we have in our eyes. Our eyes work in another way. They perceive the image or the distortion in another way, and SSIM tries to replicate or get inspired by what we have in our in the filters of our eyes, visual system. I said, okay, let me design a principal component analysis, but for images, for image distortions, using SSIM. Next, after SSIM, one of students of Zhou Wang proposed SSIM distance. So SSIM was a measure for saying how much two images are similar to each other visually, not in terms of mean squared error. There was also proposed an SSIM distance, which was a metric, distance metric, like a mean squared error, but just for visual inspection. And then I used SSIM distance in the formulation of PCA in order to propose image structural component analysis. So I proposed this optimization problem. I said, okay, rather than what does PCA do? PCA says, assume I have X. I project it onto some subspace using projection matrix U. And then I reconstruct it back by U transpose X. I want the distortion between X and U transpose X to be minimized. In other words, what PCA does is this: X minus U transpose X mean squared error. Okay, where we want to find U. And also PCA says I want the projection matrix to be orthogonal. This is the formulation of PCA. What I did was replacing the squared L2 norm by SSIM distance. So this was the only difference. Also, I divided, inspired by what we have in image processing, we usually we consider the blocks of the image rather than the whole image by itself. So we have a filter kernel, which is slided over the image. So I said, okay, let's divide the image into B blocks. Okay, and this might say bring something in your mind. Oh, I'm just making the problem distributed, so I'm having B optimization variable. Rather than having one U, which we have in PCA, let's have BU matrices. And now here in this optimization problem, my optimization variable is not a vector anymore. It's a matrix. Okay, therefore it means that my gradient is a matrix. My gradient is not a vector in this problem. Okay, because the dimensionality of gradient is the same as the dimensionality of your optimization variable. And also I have these. So I have B equality constraints, and this is a distributed optimization problem. Let's use ADMM for solving that. And as you see, I also said this in this slide, that ADMM is used a lot in signal processing. Where was that? Here. In machine learning and signal processing papers a lot, because you can make the problem distributed a lot, especially in image processing. You usually have blocks of image, right? So you can see the use cases of distributed optimization. That's an interesting thing. That's here, for example. And by the way, X here, X hat here is just the block, the ith block of the image, which is centered. So I remove its mean from it. It's the average of the pixels. And then I have this. So I convert this to this. How? I'm saying that let's embed this constraint. So these are actually B constraints, but I have the summation over B already here. So I'm embedding the constraints into the cost function as hard penalty, where H is the indicator function for belonging its variable to orthogonal matrix cone. And also, this is the actual cost that I had, all right? And I'm using the same technique that I told you here. So I'm replacing X with Z, right? Here, with Z. Here, I'm replacing U with V. And then I'm setting U to V. So it means that U equals V, right? I'm bringing V to the other side. So U minus V equals 0. And V is just a collection of all V's. So I have V1 to VB. And I have U1 to UB. And this means U1 equals V1, U2 equals V2, etc. And this is the SSIM distance that I was talking about. You can see the paper 19 for that. And as I said, U and V are the collections of the VIs and UIs. Now let's solve this using ADMM. I formed the augmented Lagrangian. Here is the augmented Lagrangian. This is the cost. This is the, do you remember the simplification that we had? Where was that? Here. Here. Something like that. Here. If you, but we only have equality constraints. So the simplification is easier. I think the previous simplification works for us here. Here, in this simplification. So we also have a constant, which is here. Here, we have a constant. This is the augmented term in the augmented Lagrangian, and this is the constant. So as you see, I have said, so I have a change of variable. Do you remember? We had a change of variable in ADMM. From nu to u. Where did we have it? Here, for example. We had change of variable. So I'm also using a change of variable. Change of variable here. From lambda to j, doesn't matter. The naming doesn't matter. When you propose your algorithm, you can name the variables. You are the owner of the variables. And then you have u, v, and j. And this is ADMM. Now let's solve it. Equation 42, I know it's simplified to the, so equation 41 and 42 can be seen as proximal mapping, as we discussed here in this slide, in this slide here. And I know that as zi is for the embedding of the constraint using indicator function, I can use projection for that. So I solved that using projection onto the orthogonal cone by setting its singular values to 1. And then this is the result. This is the result. For example, I made a data set using Lena image. Lena is one of the standard images in the image processing. So this is the original Lena image, and this is the contrast stretch. The contrast, you can work with histogram of the image. So I stretch the contrast. Here I added Gaussian noise. If you zoom, you will see that there is Gaussian noise here. Here I increased the luminance. Sometimes in your images, especially in analog images, the camera doesn't flashes a lot, and you'll have luminance enhanced. Also, I have Gaussian blurring here, salt and pepper here, and JPEG distortion, because JPEG is a lossy compression. It's a lossy compression algorithm, so it has some loss here. And then I solved that. Here are, at the end, after convergence, here this is u, this is v, this is j. What was u and v and j here? I had this u and v were the primal optimization problems, and j was the dual. And as you see, j has captured the edges of the Lena. Why? Because edges usually have a lot of information in image processing. Yeah, I think you can see it even intuitively when you see a child starting to draw something. They usually don't start drawing by coloring. They start drawing by drawing the edges. For example, by drawing a house or something, by drawing the edges. And then if they want, they will add color. So it means that the edges or the high frequency in the image has most information of the image. And the low frequency, which is the color, also adds information, but it's not as informative as the edges. So the dual variable here has captured the most informative things in the image, which are the edges. And u and v, if you zoom into that and you will look at them carefully, you will see Lena here. I can see the hat here. I don't know if you can see here. I can see here, but you need to look carefully into that. So yes, that was one of the examples of ADMM. There you can find a lot of examples of ADMM in the literature, and it can be used in industry too a lot. Some slides of this slide deck are inspired by Professor Stephen Boyd, and also our tutorial has the materials of this slide deck. Let's go through the references very quickly. The ones which I remember, the ones which I don't remember, please look at them in the slide deck. So here, alternating minimizations converge to second order optimal solutions. I think it was one of the methods which were being developed into ADMM. We also have a paper on non-convex optimization for machine learning. I think this is a good paper which talks about alternating optimization as far as I remember. So we have the decomposition principle for linear programs 1960. This is one of the old methods being developed into ADMM gradually. Also here, mixed variables programming problem. And here we have generalized Lagrange multiplier method. I think this was a paper, as far as I remember, in 1963 for augmented Lagrangian. And we have, so I don't remember what this was for. The method of multipliers, do you remember? The method which we, here, method of augmented, here. Augmented Lagrangian method of multipliers was proposed by this paper, by paper 8. And then let me go through these very fast. Okay, this is for federated learning. You can see it's a good federated optimizations. Also, this is a good survey paper on federated learning if you are interested in that. Also here, again, another paper for federated learning, which is related a lot to the distributed optimization. Here, this is one of the papers in image processing, which has used ADMM. So Oleg Mikhailovich is a professor here, and also Edward Versky is a professor at University of Waterloo, Department of Mathematics. Oleg Mikhailovich is a professor at the University of Waterloo in Department of ECE. And Daniel Otero was their PhD student. Now he is, I think, in Brazil, I guess. He's a professor now. They proposed this. Also, this is my own paper on the image structural component analysis, which I talked about. Edward Versky and Zhou Wang had a student named Brunet, which proposed SSIM distance. It's a very nice paper. I really enjoyed reading that. You can look at this. It's a theoretical paper on that. Also, this is our tutorial on optimization problem. Okay, now this distributed optimization is over. Is there any question before we move on to the next topic? No? Is everything clear? Not yet. Okay. So let's go to, okay, someone else said, yes, all good. Okay, great. Now let's move to non-smooth optimization, the next topic. So far, what we talked about, we assume that the cost function and the optimization problem, they are differentiable, right? And they are smooth. So when it's smooth, it means that you can take the derivative until infinite number of orders. Especially, so in mathematics, when you say C1, it means that for one derivative, it's a smooth. But maybe for the second derivative, it might not be smooth. When you say C2, this is a set of functions which is whose first and second order derivatives are defined, and they're smooth for first and second order. But for the third, it might not be smooth. Against C3, we also have until C infinite. C infinite, it means that it's a smooth. It's actually smooth for all orders of derivative. So usually we assume so far that f belongs, the function f, the cost function belongs to C infinite. Now, what if it's not belonging to C infinite? Especially if it's not belonging to C1, then it's actually a very big pain in the neck. Because if it's C2, but we can deal with it somehow because we can take derivatives. So gradient is defined. Also Hessian is defined. Maybe third order derivative that is not defined. But if it's not in C1, we can't even do the first order derivative, which is crucial for optimization for both first order and second order optimization algorithms. Now let's what we should do. Okay, introduction of non-smooth function. So these are examples. Here, in all of these areas, the function is a smooth, except here. In this point, it's not smooth, right? It's like, for example, absolute value function. Here also, it's smooth here, not smooth in this point. In these cases, we need non-smooth optimization. Okay, now let's see what we should do for these cases. So Lasso regularization. I think we already mentioned Lasso in several sessions ago. What was Lasso? Do you remember? What was Lasso? Do you remember, guys? So Lasso was L1 norm. So usually when we have L1 norm regularization term, it's a Lasso. So like this, in equation 3, you can see it. So we have a cost plus some regularization term with L1 norm. Why do we do that? We are putting a soft penalty here because we don't want X to, maybe in machine learning language, we call it overfit. We don't want X to be overfitted, or our model to be overfitted on X, or we don't want the X to explode, because when X becomes very big, the L1 norm also becomes big. So the penalty is on the magnitude of X, but with L1 norm. We can have the penalty on magnitude of X with L2 norm or any norm, right? But we usually use either L1 norm or L2 norm. We already talked about that. L2 norm has its advantage and disadvantage. What are the disadvantages and disadvantages? When we have L2 norm, it's differentiable. Squared L2 norm. We usually use a squared for L2 norm because L2 norm might not be convex and we can't take derivative of it easily. But a squared L2 norm, recall this formula. Squared L2 norm can be written as X transpose X, recall preliminaries that we talked about. And this is a quadratic function. So it has very good properties. It's convex. It's a smooth. And in this case, it's unimodal also. And I think by convex is, or we know that it's unimodal, because if it's not unimodal, it's not convex. So it's smooth and it's very good. It's very good. However, its disadvantage is that, and by the way, another advantage is that we can take derivative easily, because we know that the derivative of this is X, right? However, the disadvantage is that it's very bad for outliers. We'll discuss it in a few slides, I guess. Why? We'll see that. But it's very bad for outliers, for anomalies or outliers, which are very away from the mean. Assume that this is the mean. This is the mean, for example, mean or average of your data. And this is L2 norm. When some data comes very far away from mean, it means that it's an outlier of this distribution. You can see its L2 norm explodes. It's very big. So it's very bad for L2 norm. I think it's easily understandable because when you have X squared, because X transpose X is like X squared, right? In a scalar world. And compare it to X, which one explodes more for outliers? Of course, X2. So assume your outlier is some number. If you feed it to X, it's not as big as X2. That's the thing. That's the disadvantage of squared L2 norm. However, also L1 norm. L1 norm doesn't have this disadvantage. We'll see why. It explodes with slower rate. So if it's L2 norm, L1 norm is like this. This is squared L2 norm, and L1 norm is like this. As you see, for this outlier, L2 norm is here, L1 norm is here. Here. Which one is bigger? Of course, squared L2 norm. So squared L2 norm explodes more for outlier, but L1 norm doesn't explode that much. So it's not that much, it's more robust to outliers. That's a good thing. Another advantage of L1 norm is that it is sparse. Do you remember? We talked about that. Using the diamonds that I think two sessions ago or 3 sessions ago, I drew some the unit ball of L2 norm and L1 norm, and I showed you that especially in large dimensionality, this diamond has a lot of edges. Consider a multidimensional space which has a lot of diamond edges, and when your cost function touches your diamond, many of the other coordinates become 0 at that point. It means that your problem becomes very sparse because your solution to the optimization problem becomes sparse. So, and we talked about that according to the Benyamin sparsity principle, as well as Occam's razor in philosophy or logic, sparsity usually works very well. So L1 norm also works very well for sparsity. However, its disadvantage is that it's not as smooth. L1 norm in one dimension is absolute value function. It's like this. So in this point, it's not smooth. You can't take derivative. Derivative is not defined in this point. That's a problem. Calculating its derivative is a pain in the neck. Now, okay, with this introduction, let's talk about Lasso regularization. The L1 norm can be used for sparsity. We talked about it several sessions ago using the unit balls, which was proposed by Tipshirani at Stanford University. Sparsity is very useful and effective because of Benyamin sparsity principle, which was proposed by Tipshirani and Hasty at Stanford University, and also according to Occam's razor in philosophy and logic, which says that the simpler explanation for a phenomenon is a better solution, a better explanation. If x equals, it's a vector, assume x is a vector with elements x1 to xd, okay? And for having a sparsity, we should have we should use subset selection for the regularization of a cost function. Assume I want my problem to be sparse. What we should actually do, we should use this. We shouldn't use L1 norm first. L1 norm is an approximation to this. I will talk to you about it. But we should use this. This is not a norm. Sorry, but we should use this. This is not a norm. We call it L0 norm, but with quotation, double quote. Why? It means that it's actually not a norm. So this is how we call it, L0 norm with quotation. Why? Because it's not a norm. Because it doesn't satisfy the norm properties. Do you remember what were the norm properties? Recall the preliminaries. I think there were several of them. The most important one, I think, which is not satisfied here, is triangle inequality. Do you remember? So L0 norm, which is not a norm actually, what does it do? Its formula is here. It counts the number of non-zero elements. So here, it's an indicator function. What is the indicator function here? The indicator function is not like the indicator function in optimization. It's 0 if xj is 0, otherwise it's 1. So when we have a summation over this, it means that how many non-zero elements this vector has. This is called subset selection, this L0 norm with double quote. So we use that as a penalty. It means that we want to have a sparser solution with many zero entries. Okay, according to paper 5, you can see in the references, the convex relaxation of L0 norm with double quote or subset selection is L1 norm. So it's approximation or relaxation of L0 norm, which is not a norm, is L1 norm, which is actually a norm. Therefore, we write the regularized optimization problem as this. So we convert equation 1 to equation 3 because we want the penalty to be a norm. The L1 regularization is also referred to as Lasso regularization. And Lasso stands for this. It's least absolute shrinkage and selection operator. As you see, it is selecting. Also, it is shrinking to become sparse. And why does it have absolute in its name? Because it's like absolute value. In L1 norm in one dimension is like absolute value. And least, why? Because do you remember when we said, for example, if the regularization term is a squared L2 norm, we usually call it least squares problem. So when you minimize squared L2 norm, it's that optimization problem is also called least squared problem optimization. But when you have L1 norm, you are minimizing L1 norm, you call it least absolute optimization, something like that. That's the reason for Lasso name. Okay, and papers 6 and 7, you can see that. I think one of them is proposed by Tip Shirani. Different methods exist for solving optimization problem having L1 norm, such as approximation by Huber function. We are gonna explain all of these in the next slides. Approximation by Huber function, proximal algorithm, which we talked about in 2 sessions ago, or soft thresholding. Do you remember we introduced soft thresholding 2 sessions ago, or coordinate descent. We also introduce it here. And subgradients, we also introduce it in this session. These are different methods, various methods for solving non-smooth optimization problem, such as L1 norm. Okay, the first one, which was approximation by Huber function. For Huber function, we need to define something named convex conjugate, which is an important thing in optimization world. And then we'll use that for Huber function. How do we see that? Okay, let's talk about convex conjugate. What is that? Consider this figure that we are having, showing a line which supports the function f. What does support mean? So when you have a function like this, the tangent line to it is a support for this, because the whole function f is on one side of this line. So this is a support line. When we are saying support line or support hyperplane, because in multiple dimensions, it's a hyperplane. It means that it's a tangent hyperplane on the function where the function is only or solely on one of the sides of the hyperplane, okay? And that's called the support hyperplane. This figure shows a line which supports, so this is not the support hyperplane, this is a support hyperplane, right? F meaning that it is tangent to the function and the function upper bounds it, okay? Upper bounds it means that it's only on one side of it. In other words, so it's all, the line is always below it, or the hyperplane is always below the function. In other words, if the line goes above it, above where it is like this, it will intersect the function in more than one point. Here it's tangent and it's intersecting in only one point. But when it goes above, it will intersect in more than one point. Now let the support line be multidimensional to be a support hyperplane. Okay. For having this tangent support hyperplane with a slope y and intercept beta, okay, consider this is a hyperplane. It's a slope, let it be y. As it is a hyperplane, its slope is a vector in d dimensions, right? But in its intercept is a scalar. So you can write the equation of this hyperplane as this: y transpose x plus beta. Y is the slope, x is the variable of the line, and beta is the intercept. And we set it equal to f. Why? Because we want to find the tangent point where it is intersecting here I'm talking about this point, where it is intersecting the function. Okay, if we rearrange this equation, beta becomes this. Okay, now we want the smallest intercept. What we want to find the smallest intercept, okay, for support hyperplane. Why? If you consider this hyperplane, you will understand why I'm trying to find the smallest hyperplane. It's intercept, sorry. When you, so how should I talk about this? Assume this is a support hyperplane. This is a support hyperplane. Maybe this is a support. All of these are support hyperplanes, but I want to find the one which has the smallest beta, which has the smallest intercept. Beta. The smallest beta, okay? So beta star is minimized f, so this is the equation of beta. This is the equation of beta. Sorry about that. This is the equation of beta, and I want to minimize that with respect to x. I can write it as minus maximize. You remember, recall preliminaries. We can convert minimization to maximization, but we need a minus behind it. Minus max of, again, its inside should also be minus of that. So f of x minus y transpose x becomes y transpose x minus f of x. Now we found this. I'm repeating it here. What is convex conjugate of function? It's actually related to this. It's equation 4. The convex conjugate of a function f is defined as this. So when we have a function f, we can say y transpose x minus f of x, maximize it. This is supremum. Supremum is a generalization of maximum, recall preliminaries, over x. And this f star is a function of y, actually, because we are not maximizing over y, we are maximizing over x, so x goes away, but it's actually a function of y. So f star of y equals this, and this is convex conjugate of x. Therefore, we define, now compare these two. You can see that we can say f star of y equals minus beta star. Right, to have the convex conjugate defined above. Okay, the convex conjugate of a function is always convex, even if the function itself is not convex, because it is pointwise maximum of affine functions. Do you remember? This is a affine function. This is a affine function, and we have multiple of them, and we are having a supremum of the maximum of this. I said we have multiple here. In this figure, I said we have multiple hyperplanes, support hyperplanes, and let's find the one. So we have many of these support hyperplanes inside, and we are finding the one maximizing over x here. We have a pointwise maximum of affine functions. It means that it's always a convex function. Okay, now, so we had this convex conjugate lemma. The conjugate or convex conjugate of a convex conjugate of a function. So if you take convex conjugate twice, you will have f star rather than 1 star. Then it becomes supremum of x transpose y minus fy star. So the convex conjugate becomes the function again as an input of the convex conjugate, and the variable becomes y. Therefore, the variable of f star becomes x again, right? Okay, it is always a lower bound for the function. That's interesting. F star is always less than or equal to f. I'm not providing the proof here. I'm just showing the lemma. Okay, you can look up the proof in the internet. If the function f is convex, then we have f star equals f. That's interesting. So if it's not convex, f star is always a lower bound for f. But if the function is convex, it's actually equal. So by taking convex conjugate twice, you will reconstruct the function again. Hence, for a convex function, we have this. So if the function is a convex, then f of x, we can write it equal to the convex conjugate. So because this is f star. Okay, that's an interesting thing. Now I'm gonna use this in order to define the Huber function and all of these things for solving the L1 norm optimization. Okay, the convex conjugate of L1 norm is this. I'm gonna prove this here. So what does it mean? For f of x equals L1 norm of x, f star y equals if the infinite norm of Chebyshev norm of y is less than 1. So if it means that if we are inside the unit ball of infinite norm, it is 0. Otherwise, it's infinity. Okay, now let's prove it. We can write L1 norm in this way. Why can we write it in this way? So f of x equals L1 norm of x is maximum of x transpose z. So I'm introducing some variable named z, but z should be in the unit ball. Consider this. This is the unit ball of z. So assume z is, I don't know, 2-dimensional. So x is 2-dimensional. So we are inside, we are inside this unit ball. So -1, 1, -1, 1. Okay, now we are saying that x transpose z. So when we are saying that, assume, let me recall that because I thought about it a week ago. Let me recall it. Yes. Okay. Yes. So here, for example, here, because we want to maximize over z, right? We want to maximize over z. So here, this, I can't draw with this very well. Sorry about that. I'm trying my best. So in this point that I'm pointing at, okay? So here we have the maximum z, and assume here, if you have this point, what is this point? This is 1, 0. Am I right? This point that I'm pointing at. Here, if you have the dot product of x and z, x transpose z, then it will capture you x1, but x2 becomes 0. So because 1 times x1 plus 0 times x2 becomes only x1. So it only is capturing x1, exactly like what we have in L1 norm. In L1 norm, do you remember, in sparsity especially, it when we are in the edge of the diamond, many of the coordinates become 0, similar to this case here. So when you are saying that z transpose x, it's making the other coordinate 0, and that's an interesting thing. So we are relating L1 norm to L infinity norm. Here is L1 norm, this is L infinity norm, and they are dual of each other. So using the dual norm of L1 norm, I'm defining L1 norm again. You can write it. If you think about this equation, you will see it's correct. Okay, now using this in equation 4, this was equation 4, I'm repeating it here, which was the convex conjugate, results in equation 7, which is this we want to prove, right? Okay, why? Let's do that. Let's put this. So fy star, we know that is supremum over x, y transpose x minus maximum minus f of x. But I replace f of x with the definition here that I have. Maximize x transpose z over the unit ball of z. Okay, now what am I doing here? Okay, I'm changing the order of x transpose z and z transpose x because they are both scalar. I can change the order. And then if you see that, you will see that if y, the L infinite of y is less than 1, then this term is actually satisfied, and we'll have y transpose x minus y transpose x inside the supremum. It becomes 0. Otherwise, this term becomes infinite. Why? because this is the reason. Because this will go away. This can be a small number, and this can go to infinity. This can go to infinity. Therefore, it explodes. The only way that it doesn't explode is that the L infinite norm of y is less than 1, or in other words, when y is in the unit wall of infinity norm. Then these two terms become equal to each other. So supremum of 0 is 0. And then this is the proof for this. Now we are going to use this, you'll see, for Huber function. But before that, okay. Yes, here. Huber function, smoothing L1 norm by convex conjugate. How? We'll see that. Lemma, gradient in terms of convex conjugate. For any function f, we have this. This is a lemma. I'm not providing the proof here. Gradient of f is argmax of x transpose y minus f star y, where y is in the domain of f star, okay? Now we saw that the convex conjugate of f, we just proved that in the previous slide, is this. According to this equation 8, which I gave to you without proof, we have gradient of f is argmax of this for L1 norm. Why? Put this inside this. So rather than f star y, have this. If it's 0, if the y is in the unit wall of infinity norm, then we'll have argmax of x transpose y, because this becomes 0. This term becomes 0. Otherwise, this term becomes infinity, and it will explode the cost inside the argmax, right? It's not good. So we'll have this. For x equals 0, we have this. Now, in this function, let x be 0. So it's argmax of 0, which has many solutions. Because y can be anything, right? Y can be anything, not one thing. Because when you are saying max of 0, it's 0. But when you are saying argmax of 0, it can be for any argument of y, you will have maximum of 0, because you're maximizing a constant. Therefore, it has many solutions. Therefore, at x equals 0, the function L1 norm is not differentiable. This is another proof for why L1 norm is not differentiable at x equals 0. If you want to imagine it in a scalar, as a scalar in one dimension, L1 norm is reduced to absolute value function. Of course, we know that in absolute value function, at 0, it's not as smooth. But when we go to many dimensions, this is the proof why at 0 it's not differentiable. It's not smooth because the gradient at this point is not unique. Okay. Now let's see how we should tackle that. We can smooth L1 norm at x equals 0 using convex conjugate. So the first technique to handle non-convex optimization is to smooth the parts which are not smooth. So assume you have, for non-smooth function. So when you have non-smooth function, you want to do optimization, you find the points which are not smooth, and then you make it smooth at those points. For making it smooth at those points, you need convex conjugate, which we talked about. And you can use convex conjugate to define Huber function for L1 norm. You'll see how. We saw that the convex conjugate of L1 norm is this. And let x be d-dimensional. So we know that by definition of L1 norm, it's just summation of absolute values of its coordinates. We can use the convex conjugate for every dimension. For every dimension. Now this y becomes a scalar, yj, for the jth dimension. So this becomes simplified to this, if yj is less than 1, rather than the infinite norm of y, we'll say if the absolute value of yj is less than 1, it's 0, otherwise it's infinity. Okay, interesting. Now, according to equation 6, which I have repeated here, do you remember what was equation 6? This this lemma. Recall this lemma that we talked about. Why? We said that f for convex function, f is equals to f star star, and we know L1 norm or is a convex function. Therefore, equation 6 holds for that. So we can use that. I'm repeating equation 6 here. Okay, we have this. Now I'm putting equation 9 inside this equation, and I get this. How? So I'm saying that this is supremum of y, supremum over y, x transpose y, because as we are talking elements wise now, becomes xj yj, and f star y, we are talking about elements wise, so it's f star yj. According to this equation 9, it's maximum of xj yj. Why? Because f star yj should be 0, otherwise the cost explodes. So it's maximum. I'm changing supremum to maximum. Maximum of xj yj when, and this is the, I'm using this here, right? Because only when absolute value of yj is less than 1, this term becomes 0. Okay, but this is not unique for xj equals 0. Hence, we add a mu strongly convex function to the above function to make the solution unique at xj equals 0 also. Why isn't it unique at xj equals 0? Let's talk about this. So consider this, the right-hand side I'm talking about. I think it's a bit, let me erase some things here so you can see it better. Okay. Now consider this, the right-hand side. When set xj to 0, it becomes maximum of 0, a constant 0 for yj less than 1, absolute value of yj less than 1. It's a maximizing a constant with respect to yj. It can be any yj inside the unit ball of yj, right? Therefore, it's not unique. Let's make it unique at xj equals 0. So we can add some term to this, and you will see. This added term is named proximity function, defined below. Okay. A proximity function py for a closed convex set is a function which is continuous and strongly convex. We can change equation 6. This was equation 6, which I have repeated here. We can change equation 6 to this. So what am I doing? So I have supremum again here. X transpose y the same, f star, but I'm adding this term. The third term in equation, where mu is greater than 0. Do you remember? It's very closely related to mu strongly convex, which we had in preliminaries. Okay, now recall equation 9. Equation 9, which we had here. I have repeated it here. Using equation 10, which we have in this definition of proximity function, we can have this. Now let's talk. I'm deriving for you the Huber function, deriving it. So we have absolute value of xj. Let's see what are we doing. So equation 10 is this. So I'm saying that the right-hand side is the right-hand side of this equation, supremum of y. X, so but this is element-wise, so x transpose y becomes xj yj, and f star y becomes f star yj, and this is mu py here. Here, yes, I'm using yj squared. It needs to be a convex function, and here. So what is f of x for element j? Because we are doing element-wise, it's absolute value of xj for only element j. Now using equation 9, this becomes, when does it become 0? Otherwise the cost becomes explodes. When yj is in absolute value of yj is less than 1, according to this constraint. Okay, that's correct. Now we can see that this is equivalent to this. Why? Because when xj, absolute value of xj is less than or equal to mu, what happens? If absolute value of xj is greater than 0, let me mu. I need to think about it, but I'm sure that you can go from here to here. Okay, this is the Huber function. This is the Huber function. This approximation to L1 norm, which is differentiable everywhere, including at xj0. Why? Because recall that we use this proximity function, we added that, so at 0 it also becomes unique. It wasn't unique at 0, but by adding that mu term, which is here, we made it also unique at 0. This is a Huber function. This is called Huber function, proposed by Huber, who was a scientist. Note that Huber function is the Moreau envelope of the absolute value. Moreau envelope, we define that in the proximal mapping slides. Huber function, I'm defining it here. So far we were deriving the Huber function. Now this is the Huber function. Huber function and pseudo-Huber function. This is the Huber function, which we derived in the previous slide. This is the pseudo-Huber function, which is an approximation of the Huber function itself again. And mu is greater than 0 according to the proximity function here. Okay. The derivative of these functions, I'm going to show you what Huber function is like in this slide. But let me first define it. The derivative of these functions is easily calculated. And that's an interesting thing. Why did we use Huber function? Why would we define? Because we said that L1 norm, we don't have derivative for it at 0. Let's make it smooth by Huber function. And now we know that the derivative of Huber function is already calculated. It's very easy. Its formula is very easy. It's like this. For example, the derivative of Huber function, derivative of this is this. What is this? If absolute value of x is less than some value mu, it's x over mu. If its absolute value is greater than mu, it's sine of mu, sine of x. If x is positive, sine of x is 1. If x is negative, sine of x is -1. Now let's see the Huber function. Okay. This is L2 norm, a squared L2 norm. This is L1 norm. Recall the discussion that I had several minutes ago, saying that for outliers like this, L2 squared L2 norm explodes, but L1 norm is a small. Interesting. L1 norm is a small, but the squared L2 norm explodes for outliers. Also, outlier might be here, right? So L1 norm is robust to outliers. Also, L1 norm is good for sparsity. However, here at 0, L1 norm is not a smooth. L2 norm, however, is a smooth. Okay. Now let's see the Huber function here. What is B? Comparison of L1 norm, the absolute value in R1, because here we are assuming that we are only one-dimensional, right? One-dimensional. And the Huber function. This is the Huber function for different, here I'm talking about this figure, Huber function for different mu values. So let me see. The orange one is L1 norm. No, sorry, not the orange one. Sorry, I apologize. The blue one is L1 norm. Okay, according to the legend, I'm saying that. And I'm increasing mu by this. So mu is increased. Here mu is increased. So by going down in this figure, I'm increasing mu. It means that when your mu is small, your approximation is more correct, more exact. But when you increase mu, your calculation of Huber function is easier. However, you lose accuracy in your approximation. So less mu is more accurate, but the calculation of the Huber function and its derivative is harder because of this. It's, for example, its derivative. When you set mu to be a small number close to 0, then this hardly happens. But this happens a lot, the second condition. It means that you're almost, in most cases, you are actually approximating the derivative correctly. Why? Because do you remember what is the derivative of the L1 norm except 0? It's actually this. It's a sine function. But at 0, it's approximating it using this. When mu is close to 0, it means that the approximation range here is a small. So your approximation is more exact. However, when you increase this range by increasing the mu, it becomes easier to calculate. However, the approximation is lower. Okay. And as you see, interestingly, here at 0, although L1, which is a blue curve, is not a smooth, however, the Huber function is smooth at that point. And it's interesting. Okay, now let's see the figure C. Comparison of L1 norm or absolute value in R1 in scalar and the pseudo-Huber function. So this is this blue one, again, blue curve is L1 norm. And these other colors here in figure C are pseudo-Huber. So figure B was Huber, figure C is pseudo-Huber function. And also here, let me see in the legend, I'm increasing, by going down in the figure, I'm increasing mu. Okay. Again, by having a small mu, the approximation is more correct. And as you see, there is a slight difference in the behavior of Huber and pseudo-Huber functions. In the Huber function is always a lower bound on the L1 norm. However, for some mu values, pseudo-Huber might go above L1 norm. But in many mu values, it's actually lower bound of L1 norm. But for some mu values, it might go above that. So that's one difference between Huber and pseudo-Huber. Again, at 0, you can see that although L1 norm is not a smooth, Huber and pseudo-Huber are smooth. Okay. These two functions are smooth, so they can approximate L1 norm smoothly. This figure shows that Huber function is always upper bounded. As I said that, we can also see the approximation of Huber function is better than the approximation of pseudo-Huber function. Yeah, Huber is better than pseudo-Huber in terms of approximation accuracy. However, its calculation is harder than pseudo-Huber. Why? Compare equation 11 and equation 12. Of course, equation 12 is easier to calculate, but its approximation is less accurate. Moreover, the figure shows a smaller positive mu is better approximation. Okay, we talked about that. So far, we talked about how to smoothen the L1 norm. I understand that some slides of this slide deck are hard and difficult a bit. Don't think that it's only hard for you. It's all hard for me and others too. But these are because we are in the last sessions of this course, these are the advanced topics of the optimization. So we are getting into the harder topics of the optimization, and there is no exam on that. So try to learn them with joy. Okay, now soft thresholding and proximal methods. Then the other way to handle non-smoothness. I say this, and then we'll go for a break. Okay. So soft thresholding and proximal methods. How to do it? Proximal mapping was introduced in 2 sessions ago. Do you remember? This was the proximal mapping. Okay. We can use proximal mapping of non-smooth functions to solve non-smooth optimization problems by proximal methods introduced before. So we can use proximal mapping. How? For example, we can solve an optimization problem containing L1 norm in its objective function, which is not a smooth, using the proximal mapping of L1 norm, which is subthreshold. And recall 2 sessions ago, which we proved that the proximal mapping of L1 norm is subthresholding. And we showed that it's this. This is the subthresholding. We should do it element-wise. Proximal mapping of the jth element of proximal mapping is this. And we can write it in this. We showed that these two are equivalent. We discussed it. And we named it to be subthresholding, and it's an element-wise function. Okay, it says that for if the value of that element is greater than lambda, approximated with this line. If it's less than lambda, approximated with this line. If it's between minus lambda and lambda, let it be 0. And as you see, this range from minus lambda to lambda is actually approximating the absolute value or the L1 norm around 0. Again, this range should be small. So the smaller the lambda, the better the approximation, right? So this is a better approximation than this, because it actually needs to be something like this when lambda is exactly 0. It needs to be like a line. But if we set lambda to be 0, then we'll not have I'm saying that we'll recover, I think, L1 norm, which is non-smooth at 0. So we need to have some lambda, but lambda should be small. Lambda should be small to have a better approximation. And also, I think you should note 2 things about so 2 things which are common about these methods. First thing, they are doing element-wise. An interesting thing which you should note is that when it's a non-smooth function, usually different approaches like proximal methods or Huber function or these things, they're being applied on the function element-wise. Why? Because it's easier to handle non-smooth functions element-wise rather than vector-wise or matrix-wise. Okay. So let's work on the scalars, the scalar values of the elements. That's one thing which you should note in common between different methods. Also, another thing is they have a range. So around the smooth, non-smooth point, here in L1 norm it's 0. Maybe in another function is some other point. You usually have a range and some parameter which defines how large this range is. And usually the smaller the range, the better approximation you have. And that's an interesting thing. Okay. So here we have any proximal methods such as proximal point method. And so now using this proximal mapping, you can use proximal point method or proximal gradient method. Do you remember we introduced these 2 sessions ago in proximal mapping algorithms? You can use any of these, but using proximal mapping of L1 norm. Okay, that's interesting. For solving the regularized problem 3, like minimize a cost function regularized by L1 norm, which is optimizing a composite function, we can use proximal gradient method. Do you remember? Recall that? It says that for composite functions, we can use proximal gradient method where we are using the proximal mapping of the regularization term. Here, the regularization term is L1 norm, so we can simply use the subthresholding. Interesting. Okay, before we continue with the other methods for handling non-smoothness, including coordinate descent, let's have a break and come back at 9 maybe. Is that fine? Okay, great. See you at 9. Okay, let's continue. So, okay, coordinate descent. Again, this method, similar to other methods which handle non-smoothness, they work on elements, or they're element-wise. In other words, they are coordinate-wise, so they work on coordinates. This is another algorithm for that. Assume that this is the vector x. For solving minimization of f of x with respect to x, coordinate method, you can see paper 10, updates the dimensions or coordinates of the solution 1 by 1 and not all dimensions together at once. So again, it's using alternating optimization introduced in the slide deck for distributed optimization. Do you remember? Recall previous session. We said alternating optimization alternates between several variables, right? Now here, coordinate descent uses alternating optimization, but the variables now are the coordinates. See? So once it updates the first coordinate and considers the other coordinates to be a constant, equal to their previous value. And then it considers the second coordinate, the other coordinates to be constant, equal to their previous one, but x1, we use the updated x1 here because x1 is already updated. Here also, for x3, for example, we use x1 k plus 1, x2 k plus 1, but x4 k, x5 k until xdk. So we do until this x for xd, all of them are x ik plus 1. So we do it and then we go from scratch again. We do it iteratively. In each iteration, we have these updates. So this is coordinate method. And we do it until convergence of all dimensions, x1 to xd. Okay. Note that the update of every dimension uses the list update of previously updated dimensions. The order of updates of the dimensions does not matter much. Okay. And the idea of coordinate descent is similar to the first of it's using alternating optimization, and also it's similar to the idea of Gibbs sampling, where we work on the dimensions of the variable one by one. Do you know Gibbs sampling? Does any one here know Gibbs sampling? So in Gibbs sampling, we also sample, for example, if we have several dimensions of variables, so we sample for one of the dimensions, and then for each dimension or each variable, assume that we have this a mixture. How should I call it? A multivariate distribution x1. This is Gibbs sampling x1 2x d or x and whatever, doesn't matter. We have several variables for a multivariate distribution, and P stands for PDF of the distribution, probability density function, PDF. Okay, and then we want to sample from this multivariate distribution. Gibbs sampling says that okay, you can sample for each dimension of this multivariate distribution, for each variable of this multivariate distribution one at a time, using the same approach that we have here in coordinate method. So first sample for x1, and then sample for x2, then until you sample for xd, and then go again back to x1 and then x2 and x3, and go do it iteratively until convergence. After some burnout iteration, you then can accept the samples of the Gibbs sampling. This is in statistics. If you want to look at it, just it's a fun thing. So its idea is similar to, so you can see in science, many ideas are shared between even the fields of science. So here it says optimization, Gibbs sampling is from statistics. They are related to each other. And coordinate, so if we use a step of gradient descent, so for these argmins, each of these is argmin, right? We can use any optimization algorithm. Again, we need to, for each of these, we need to use solve until convergence, to remember, because it's argmin. But so if we, for example, for each of these, we need to use a gradient descent until convergence. But again, as we talked about it for ADMM and distributed optimization, we don't need, in practice, it has been shown that you can do it one step. For example, each of these can be a one step of gradient descent or something like that. So we can use one step of gradient descent or several steps of gradient descent for every of the above updates. And if you use one step of gradient descent for every update in this equation 15 for each of these lines, you use one step of gradient descent, then the coordinate method becomes coordinate descent. Its name is coordinate descent. Okay. If we use proximal gradient method, a step of proximal gradient method for each of these lines in coordinate method, then the algorithm becomes proximal coordinate descent. Okay, we already talked about proximal gradient method 2 sessions ago. We can group some of the dimensions or features together, group some of the features together and alternate between updating the blocks or groups of features. So rather than one feature or one dimension at a time, let's do it block by block. If we do so, it's called block coordinate descent. Okay. The convergence analysis of coordinate descent and block coordinate descent, you can see them in papers 15, 16, and 17. And also they show that if the function f is continuous, proper, and closed, these were defined in preliminaries, the coordinate descent method converges to a stationary point. Do you remember? Stationary point, we also defined that in preliminaries. There exists some other faster variants of coordinate descent, such as accelerated coordinate descent. You can see papers 18 and 19 for that. They are faster. Similar to stochastic gradient descent, SGD, you remember? We talked about that several sessions ago. The full gradient is not available here in coordinate descent to use for checking convergence. Do you remember in gradient descent, for example, we can, one of the convergence criteria was the norm of the gradient. However, we said in a stochastic gradient descent, we don't have the full gradient. So we can use other criteria for convergence check, or have a aggregation of some of the gradient, some of the gradients of some of the sampled points. Here we have the same issue. We should use other convergence criteria, such as maximum number of iterations or these things for convergence. Also, we can for convergence in coordinate descent, we need to every dimension to converge. So all dimensions to converge to some stable number. All the coordinate descent methods are very simple. It's very simple, and have shown to work properly for L1 norm optimization. They have used people have used it a lot for L1 norm, but they haven't. They don't have they haven't sufficiently attracted the attention of researchers in the field of optimization. People in pure optimization and many of them, such as Nocedal or even Boyd and these things, they usually don't talk much about coordinate descent. Apparently, it's not. They might not like it much because I think it has less solid background in mathematics. That's the reason. But in practice, it has been shown to work well, sufficiently well. Okay, now L1 norm optimization. We want to use coordinate descent for L1 norm optimization. It can be used for L1 norm or Lasso regularization optimization. So because every coordinate of L1 norm is an absolute value. Do you remember? For a d-dimensional vector, the L1 norm is a summation of absolute value of coordinates. And the derivative of absolute value is a simple sine function. You remember? It's a simple sine function, which is this. -1, this one. Okay, this is a simple sine function. One of the well-known L1 norm optimization methods is Lasso regression, proposed in 1996 by Tibshirani, which was this. Okay, this is the Lasso regression. Let's solve that. Let's solve that. Why are the labels? So we want to do regression. In regression, we have some labels, right? And X is just a matrix, and each it's n by d. So yes, n number of points, and d is the dimensionality of data. N is the number of points. Beta is a vector of beta 1 to beta d. This is I'm explaining the formulation of regression. This is regression, but regularized regression with L1 norm. It's called Lasso regression. And the regression coefficients are beta. Also, lambda is a regularization parameter. It's just for weighting. The Lasso regression is sparse because of L1 is sparse usually, which is effective because of the reasons that we talked about before. Let C be the objective function in equation 16. So let C be this. C. The objective function can be simplified as this. So we can simplify C as this. So this is half because of that. And if I'm using this squared L2 norm is X transpose X. Rather than X, now put Y minus X beta. And you will get this term. Okay, I'm using this formula. And it's a quadratic function. And then here we also have lambda beta L1 norm. Now let's consider the jth element of this objective function. Why do we do that? Because in coordinate descent, we are working on element-wise or coordinate-wise. So Cj, the jth element of C is this. Note that we are talking about X here, Xj, right? So we have, and beta j. So so here rather than, let me, here. Give me a second. First off, this L1 norm becomes absolute value. I know that. Y transpose Y, I'm not talking about elements of Y, but elements of X and beta. So Y transpose Y is the same as before. Here, let X minus J be defined as X, but we drop the XJs, okay? So we have X1 to XD, but let XJ be dropped. And beta minus J also be this, but beta J is dropped. It's the same as beta, but beta J is dropped. Then you can write this in this way. So what are we doing here? Yes. This is element-wise of this. This is element-wise of this. So this term is element-wise of this. Okay. Let me see. Let me see here. I don't remember why it was this for. Do you remember? If one of you have found out, let me know here. Otherwise, I will think about it and I will say the reason for this in the recorded session that I'm going to upload to YouTube, and I will send you the link. I will think about this term. I don't have it on top of my mind right now, and I will explain it to you in the next session. But assume accepting this term from me, this is the jth element of C. Now let's continue, not to waste time. And then for coordinate descent, we need gradient of objective function with respect to every coordinate, okay? The derivatives of other coordinates of objective with respect to beta j is 0. That's an interesting thing. So in coordinate descent here, when we are optimizing over x1, the function is constant with respect to x2, x3 until xd. The only variable which we care about is x1. Here also, we care about x2. Here we care about xd, right? Now we are considering the jth element, jth coordinate. So we are, by the way, the optimization variable is beta, right? So we are talking about beta j now. We are only for jth element, we are optimizing over beta j, and the other coordinates are just constant with respect to beta j, and their derivatives become 0. Now let's take derivative of the cost function with respect to beta j. It's for the same reason that I just talked about. Derivative of c with respect to beta j equals derivative of cj with respect to beta j. And so take derivative of this with respect to beta j. Let's do that. This is constant, so it becomes 0. This is a linear function with respect to beta j, which we have it here, this term and this term. So x transpose y, I have it here, right? And here, This is quadratic with respect to beta j, so it becomes x transpose xj transpose xj. Here is its derivative. Derivative of this is also quadratic with respect to beta, and its derivative is x transpose x, which is this term. And this is the absolute value of beta j. Its derivative is sine, right? Now we take derivative. What do? We set it to 0 for optimization. Am I right? If you compare this line with the soft thresholding function defined here, which we also derived 2 sessions ago, you will see that this is actually beta j is the soft thresholding of this function, interestingly. So now, even in coordinate descent, soft thresholding comes up. So beta j, which is the jth element of beta in the regularization here, optimization problem 16, is actually the soft thresholding of this term inside. This is a soft threshold, interestingly. So coordinate descent at the end also reduced to soft thresholding for that. So coordinate descent for L1 norm optimization finds the soft thresholding solution, the same as proximal mapping, several slides ago. We can use this soft thresholding in coordinate descent, where we use beta j's in equation 15 rather than xj's. Equation 15 here. So now, we can use this soft thresholding in coordinate descent. So now, this is for the jth element, right? This we should do it for all elements. So each of these lines become just an optimization problem. And interestingly, for this regression, Lasso regression, every line of coordinate descent has a closed form solution, which is soft thresholding. If it did, do you remember? I have said it several times in this course. When you have an optimization problem, the first thing which you need to think about is that take derivative, set it to 0. If it has a closed form solution, it's done. However, we might do another step to check whether what you found is a maximum, minimum, or saddle point. So for that, you need to take the second derivative and see the direction of second derivative, whether it's facing up or facing down. If it's facing up, it means that at that point, it means that it's minimum. If it's facing down, the second derivative is negative definite. It means that it's a maximum. Otherwise, it's a saddle point. But anyway, what I said is that take derivative, set it to 0. If it's closed form, done. It's finished. If it's not closed form, then you need to do it numerically, iteratively, like first order methods, second order methods that we discussed. Here, we wanted to do coordinate descent for regression. We said, okay, let's take derivative, set it to 0. If we couldn't find a closed form solution, we had to do it iteratively using like this. However, we saw that each of these, we don't need to do a coordinate descent for, we don't need to do gradient descent for each step. We found the closed form solution for each of the dimensions, for each of these lines. Then it's done. Each of them is soft thresholding for L1 norm regression. Maybe for another problem, not a smooth problem, coordinate descent doesn't have closed form solution, and you need to do it iteratively. Okay, that's one thing interesting. Any questions so far? No? Okay. Subgradient methods. One of the most important things in optimization is subgradients. So far we talked about gradient. Now, when the function is not as smooth, we need to define subgradient. It's a generalization of gradient. So gradient is a special case of subgradient. Okay, now let's talk about it. So subgradient, we know that the convex conjugate, which I talked about minutes ago, is this, right? It's always convex. We also talked about it because it's a pointwise maximization of affine functions. If the convex conjugate f star y is a strongly convex, if it's a strongly convex, then we have only one gradient according to equation 8. What was equation 8? Let's recall that. This is equation 8. Do you remember? The lemma that we had. We said that gradient equals argmax of x transpose y minus f star y. I said I don't bring the proof here, but there is a lemma for that. Okay. Now I'm repeating equation 8 here. I'm saying that if f star y, which you can see it here, if f star y is strongly convex, then the whole thing has only one solution, argmax. So gradient of f will only have one gradient. However, if the convex conjugate is only convex, not strongly convex, then this equation 8 might have several solutions. We might not have only one gradient of f. So here the left-hand side of equation 8 is the gradient of f. The right-hand side is something, is the convex conjugate, right? Is something with respect to something having the convex conjugate in itself. If the right-hand side has several solutions, then it means that the left-hand side, which is gradient, is not unique. So gradient might not be unique. Actually, this happens exactly at the points which are not smooth. For the points which does not have a unique gradient, it means that those points are not smooth. The function is at those points is not smooth. We can have a set of subgradients. Interesting. So the right-hand side of this equation 8 has several solutions. Therefore, it means that the left-hand side is a set rather than one gradient. So we have a set of gradients, but we don't call them gradient anymore. We call them subgradients. So we have a set of subgradients are sets. I will talk about that. So consider a convex function f with domain D. The vector G is a subgradient of f. I'm defining it at the domain of x if it satisfies this. So f of y is greater than or equal to f of x plus g transpose y minus x for all y in the domain, for all y. What does it mean? Visually, you can see it here. So assume at each of these points here, we only have at each of these points we only have gradients, one gradient. Why? Let me show you. For example, at this point, the tangent is this. The slope of this tangent is gradient or derivative, right? Let's talk about another point like this. Like here. The tangent is this, and we only have one slope. We don't have several tangents. However, at this point, which is not as smooth, we don't have a tangent anymore. We can have tangent at the right-hand side of it, which is this. Also, the tangent at the other extreme, which is this. So we have one extreme slope here, one extreme slope here, but we can move this tangent from here to here. So like this, what I have drawn here. So you can have a set of lines, a set of tangents, or we can call it, let's call it tangents, a set of tangent hyperplanes or lines. Here it is 1D, so it's a line. Otherwise, it's a hyperplane. Set of hyperplanes or tangents whose slopes are upper bounded and lower bounded by the left-hand side, by the sides of that non-smooth points. If it is in 1D, we only have two sides, but if it's multiple dimensions, we have a lot of sides, right? So it has a range of slopes, but it has bound. It can't go all the way. So for example, it can't go like this. It can only go from here to here, right? The lines here to here only. So the slopes of these lines are actually a set of slopes and they are called subgradients. Subgradients, okay. And so this is the definition, and this is the visualization for subgradient. Now let's talk about this. So subgradient is one of the slopes of one of these lines. A set of these slopes or a set of these subgradients is called subdifferential. So these are the terms. I'm defining them. So the subdifferential of the convex function with domain D at a point X is a set of all subgradients at this point. So this has a slope. Let's call it S1. So it's a slope is G1, which is the subgradient G1. We have S2, G2. We have a lot of them, right? A set of all of these is a subdifferential, and we denote it by partial f of x. Partial f of x. It's a set of G, vectors G. By the way, the line I'm calling it vector G. So this, I'm saying that when I was saying slope, I was thinking about 1D, but in multiple dimensions, it's a vector. It's a vector, right? It's not a scalar. So that's why G is a vector. In general case scenario, it's a vector. So we have several slopes actually. We don't have a scalar slope. That's the thing. And G transpose Y, this is what is this? Recall equation 17, the definition of subgradient. So G transpose Y minus X is, so I'm rearranging this equation 17 by bringing f of x to the left-hand side. And so it becomes G transpose Y minus X is less than or equal to Fy minus Fx, right? This is exactly the definition of subgradient. So it means that the set of subgradients, simply it means that the set of subgradients, okay. So that the subdifferential, which is a set, is a closed convex set. Recall preliminaries. Every subgradient is a member of the subdifferential, of course, based on by definition of subdifferential. That means that G belongs to subdifferential of fx. An example subdifferential is shown in this figure. All of these is a set of subdifferential. Okay. Subdifferential for L1 norm. An example of subgradient is the subdifferential of absolute value. Now let's talk. So this is an example for subdifferential. Let's talk about subdifferential of L1 norm as an example of non-smooth function. For x is greater than 0, we only have one gradient. So one important thing which you should note is that when at the points where the function is smooth, like this point, we only have one tangent and one slope. In multiple dimensions, we have one vector slope, G. So the subdifferential has only one member, and that's the gradient. So the subgradient is the gradient at the smooth point, at the smooth point, and that is and the subdifferential is a set of one member, which is the gradient. However, at the point where the function is not smooth, we have the subdifferential has a lot of members, and each of which is a subgradient. At the smooth point, it has one member, which is the only subgradient, which is equal to the gradient. So at the smooth point, subgradient equals gradient, and the subdifferential has one member. Okay, like this here, we know that this is the absolute value. Again, elements-wise, I'm talking about element. So when x is greater than 0, it's the slope here is 1. So 1. When x is less than 1, the slope here is -1. It's exactly sine function, right? So the derivative of this is this 1 minus 1. But at 0, it's not a smooth. Therefore, we have a set between -1 and 1. Do you know why? Let's talk about it. I want to tell you, let's find the subgradients at 0. What are the extremes? What is the range of the subgradients? One of the extremes is this line. One of the extremes is this line. So we can have all lines in this range. If my pen works well, I can draw for you. All of these lines from here to here. So I can look at my hand from here to here. Bounded by the two extremes. Their slopes each slope is a subgradient, and the collection or the set of these slopes is the subdifferential. And as you see, the slope from here to here is bounded between -1 and 1. That's the reason. And as I'm talking element wise, the set is a set of scalars. So every point real number between -1 and 1 is scalar. But if we were talking about multiple dimensions, which are not here, we are not talking about multiple dimensions here. But if we were, then the set would be a set of vectors rather than a set of scalars. Here is a set of scalars because we are talking about one dimension. Okay, the subgradient of absolute value is equal to the gradient for x less than 0 or greater than 0. But at 0, we have a set. We can compute the subgradient of L1 norm because we have this. This is the L1 norm formulation definition. Recall preliminaries. We take equation 19, which is this, the subdifferential for L1 norm each element, as a subdifferential of the ith dimension, denoted by partial fi xy. Hence, for f of x equals L1 norm of x, we have this, where these times denotes the Cartesian product of sets. Doesn't matter. So we have Cartesian products of several sets. In simple words, if you can consider the subdifferential for L1 norm element-wise, like other algorithms, like other methods for the non-smooth functions, right? Okay. Subgradient, again, we can have the first order optimality condition using subgradients. Do you remember these? When we say first order optimality condition in optimization, it's exactly the rule that I call it what we do in high school. What do we do in high school? Take derivative, set it to 0. It is, in fancy words, it's first order optimality condition. Why? Because we are taking the first order derivative and set it to 0. Okay. Now let's generalize that for non-smooth. So let's generalize what we had in high school for non-smooth function. First order optimality condition with subgradient. What is it? It says, it means that when 0 belongs to the set of subdifferential. So it means that I want one of the subgradients to be 0. One of the subgradients in the subdifferential at that point to be 0. So it means that, in other words, at the optimal point, which is the minimum or maximum, whatever, 0 is one of the subgradients. Of course, here, for example, consider these and these two. In this function, it's a smooth, and we only have at the optimality point, which is this, we only have one gradient, which is 0. And this is correct for the smooth function. Now let's talk about non-smooth function. Here again, this is the optimal point, x star. We know that all of these slopes, which I'm drawing in this range, from here to here, all of these slopes are this in this subdifferential. But there is one slope which is important to me, and that's this. This slope is 0. So it means that this point is actually a minimum point. If it's convex, we know it's global minimum. If it's not convex, it might be a local minimum. But we know it's a local minimum at least, right? And that's an interesting thing. According to equation 17, so we are showing the proof now. Let's prove this. I told you the intuition of this. Now let's see the proof. According to equation 17, what was equation 17? Here, the definition of subgradient, okay? I'm repeating it here. We have this. If we have G equals 0, because when we say this, it means that one of the subgradients I want it to be 0. Now, let's set G to be 0. What happens? This term goes away. So it means that Fy is greater than or equal to Fx star. What is it? It exactly means that X star is the minimizer of F, right? It's a minimizer because for F of X star is always less than or equal to F of Y. If it's not convex, in a local neighborhood of X star, we have it. If it's convex, it's in all domain of X, this happens. It's a global minimizer, right? Okay. Now, subgradient in some example functions. Let's see that. The following lemma can be useful for calculation of subdifferential of functions. Some useful properties for calculation of subdifferential of functions. Some of them I just briefly mentioned them. For a smooth function at points where the function is a smooth, subdifferential has only one member, we talked about it, which is the gradient. So at the smooth point, we only have this. Linear combination. If F is a linear combination of some functions with weights greater than or equal to 0, then the subdifferential again is the linear combination of the subdifferentials of the functions. Okay. Affine transformation. If f of x is equals some f of f0 ax plus b, then the subdifferential of f of x a can, so it is a affine, so it's a linear operator. So you can say a transpose subdifferential of ax plus b. So this a is also multiplied to the subdifferential when we have this. Pointwise maximum. Suppose we have f of x maximum of f1 to fn, where fi's are differentiable, okay? Let I of x be I where fi equals f. It states which function has the maximum value for the point x. Let me show it with some figure. For example, like this. So we have 3 lines, and what it is saying, I think I is this, the maximum of these intersections of these. So maximum value for the point x. At any point other than the intersection point of the functions, these are the intersection points of the functions, which is other points are smooth, but the intersection points are not as smooth. The subgradient is the gradient itself, the gradient. At the intersection points of 2 functions, which is not as smooth, for example, this, we have this is the subgradient. Again, this is a linear combination between the gradient of one of them and the gradient of the other one. Of course, it's obvious why, because for example, in this figure, all of these points, the slopes of all of these points is a subgradient. So, and they are bounded by the 2 functions, by the 2 gradients from this point, this line, and this line. They are the slopes are bounded between these 2. That's the reason. In other words, it's an interpolation of the gradients of the 2 intersecting functions. Okay, subgrade again, the subgradient method. Now, so far we talked about subgradient and subdifferential. Now we are introducing an optimization method named subgradient method. Subgradient method, which was proposed in paper 20, is used for solving unconstrained optimization problems, minimize f of x with respect to x, where function f is not as smooth. That is not differentiable everywhere in the domain, in its domain. What does it do? It iteratively updates the solution as this. very similar to what we have in gradient descent. So I can say subgradient method is the extension or generalization of gradient descent for non-smooth functions. You can see, I think if you analyze it, you will see that gradient descent is a special case of subgradient method. Why? Because if you replace a subgradient with a gradient, it becomes a gradient descent. All right. So where G is any subgrade, that's an interesting thing. Any subgradient of the function in point X at iteration K. So we know that in the smooth points, at the points where the function is smooth, this equation 21 in this G becomes gradient of F. And this equation 21 is the update in the gradient descent. However, when we reach a non-smooth point, at that point, we have subdifferential, which is a set of subgradients. So we have a lot of subgradients at that point. Take one of them, maybe randomly, and it works. It works. So you take one of them, update your solution. If the updated solution is smooth, then do gradient descent again. Otherwise, if the next point is also non-smooth, take one of the subgradients. And it works with any subgradient of function. Of course, in the smooth points, we only have one subgradient, which is a gradient. Okay. Comparing this update with the update in gradient descent, it says that it's a special case of that. Yeah, gradient is a special case of subgradient method because, yes, at that point, subgradient is gradient. I already talked about it. Okay, now here. We also have C. We are having the generalization of the first order methods that we talked about for non-smooth functions. So we had gradient descent. We generalized that to subgradient method. We had a stochastic gradient descent. Now we have a stochastic subgradient method. By the way, why don't we call it stochastic subgradient descent, or why didn't we didn't call it subgradient descent? Because at the non-smooth points, it's not a descent direction anymore. Because when you're taking one of the subgradients, it might not be a descent direction. Descent means that, so ascent, gradient ascent means that at the direction of the most growth of function or the most increase in the gradient. Descent is the other way around because we have minus gradient. That's why we call it descent direction. However, in non-smooth points, we are taking one of the subgradients. It's not a descent direction at that point anymore. That's why we call it subgradient method rather than subgradient descent. Here also, we are calling it stochastic subgradient method in paper 21. So here you can see we are taking GIK. So and we are considering only one of the points rather than do you remember we have a full gradient in stochastic gradient descent, but we don't take the whole gradient, we take one of them. So we take one gradient of fi rather than gradient of f. Here we also don't take the whole g, we take one of them gi's, one of the points in the stochastic subgradient method. Compare it with this as SGD, you will see that SGD is a special case of a stochastic subgradient method. We can have also mini batch stochastic subgradient method. So we take a batch and one mini batch, which is an intermediate case between a stochastic subgradient method and subgradient method. Do you remember? And full subgradient method. With we also can have extensions of SAG and SVRG and all of these for using subgradient. That's interesting. So we can solve non-smooth functions using these methods. We'll also have projected subgradient method. Now, so far, we assume that the optimization problem is unconstrained and the function might be non-smooth at some points. Here, you are saying that what if the optimization problem has some constraint? And this is the feasibility set. Where is the feasible set? If the function is not smooth, we can use projected subgradient method, paper 22, which generalizes the projected gradient method introduced before. Do you recall 2 sessions ago? Similar to the update in the projected gradient method, do you remember? This was the projected gradient method. So we had a step of gradient descent, and then we projected after every step of gradient descent to the feasibility set. Projected subgradient method does that it iteratively updates the solution as this, similar to that. However, rather than gradient, we have subgradient. So in the smooth points, subgradient reduces to gradient, but in non-smooth points, we take one of the subgradients in the subdifferential. Some acknowledgements. Some slides of this slide deck are inspired by the lectures of Professor Stephen Boyd at the Stanford University. Also, some slides of this slide deck, especially the parts for the coordinate descent and lasso regression, are inspired by the teachings of Professor Ghojogh at the University of Waterloo, Department of Statistics. And our tutorial also has on optimization has some materials in this slide deck. Let's go through the references very fast, the ones which I remember. So this is my tutorial on regularization. You can look at it for different regularization and overfitting and these things. This is the book of Hasty and Tibshirani and Friedman at the Stanford University, which is a very good book, Elements of Statistical Learning. This also discusses lasso regression. Also, betting on sparsity principle was proposed in this, initially in this book. Now, this is about talking about Occam's razor, especially in data science and knowledge discovery. Stephen Boyd and et al., their book, Convex Optimization. Also, here, this is the paper which discusses that the convex relaxation of, I think convex relaxation of L0 norm with double coat is L1 norm. This is the paper 5. That's an interesting. Tibshirani, this is the paper of Tibshirani which proposed lasso regularization for the first time. Hasty and Tibshirani, again, they have a book, a very good book about sparsity, statistical learning with sparsity, and lasso and generalization, recently published, 2019. This is Huber. Do you remember Huber? In 1992, he proposed Huber function. Again, Boyd et al. Have some papers on proximal algorithms for proximal mapping and all of those things. Coordinate descent algorithms. This is a survey by Wright about coordinate descent methods. Coordinate descent algorithms for lasso penalized regression. It's good paper also. Proximity functions. We had proximity functions. We talked about that, I think, for Huber functions, as far as I remember. Here you can see it. Here, Gibbs distribution and Gibbs sampling. I told you, I think this is the paper which proposed in 1984, proposed Gibbs sampling and Gibbs distribution, or Boltzmann distribution for the first time, almost. This is my tutorial paper for server sampling. You can see that for sampling algorithms, especially used, you can use it for stochastic gradient descent and mini batch gradient descent. You can analyze them well with this paper. Also, convergence of coordinate descent method for convex differential minimization. This paper discusses convergence of coordinate descent algorithm. This is error bounds and convergence analysis of feasible descent points. Also, convergence of block coordinate descent. Do you remember we talked about block coordinate descent? You can see it in this paper. This efficient accelerated coordinate descent. Do you remember we said we can have accelerated coordinate descent? This is its paper. Accelerated parallel and proximal coordinate descent. I said if we use proximal mapping and coordinate descent, we'll have proximal coordinate descent. This is its paper, 2015. These are state of the art almost. Do you see that? Against Siam Journal on Optimization, one of the most important journals in optimization. Minimization methods for non-differentiable functions. It's a book. Also, non-differentiable optimization and polynomial problems. C. Non-differentiable or non-smooth optimization is an important field in optimization. Many books on them. Also, on the projected subgradient method, I said when we have constraint optimization problem where the function is non-smooth, we can use projective subgradient method. This is its paper proposed in 1998. And also at the end, this is our tutorial on optimization, which also discusses these methods. Any question, guys, before we conclude the session? So this was the end of the non-smooth optimization. The remaining topics are non-convex optimization, which is not very long, and then meta-heuristic optimization. For non-convex, I will talk about in the next session, which I will record for you. I will talk about just sequential quadratic programming, sequential convex programming, SCP, and trust regions. Also, I will talk to you about meta-heuristic optimization, also including the gradient genetic algorithm, particle swarm optimization, simulated annealing, and at the end, I'm gonna talk about Nelder-Mead simplex algorithm, which is used in fmin search of MATLAB. If it's one of the most important functions in MATLAB for optimization. This is also a heuristic algorithm. I will talk about that. I will also record a lecture. It's a bonus lecture on Riemannian optimization. So you can, this is an advanced topic, but I think that you will enjoy that. So you can optimize on the Riemannian manifolds, Riemannian matrix manifolds. I will talk about this. I will record them, and feel free to reach out to me if you have any question on those, and I will be happy to answer you. Any question?
These recorded sessions will be in the course link?
Sorry, what?
So these recorded sessions will be in the course link?
I will record them, put in my YouTube channel, and I will provide the links in the course link. Yes.
Okay, thank you.
No problem. By the way, guys, please feel free to rate me on Rate My Professor. Also, there is a feedback of the department. You can give your feedback anonymously in both Rate My Professor and in feedback system. I see that in feedback system, only 2 people have given feedback about me anonymously. I don't know their names. And also in Rate My Professor, there is no feedback. I will appreciate it if you please give me feedback. I want to know what you think about the course and me and how I teach. Thank you very much.
Surely we'll do that. Thank you.
Thank you very much. I appreciate it. Any question? No? Okay, so see you next session next week with your presentations. Good luck with that. And yeah, thank you. I think I enjoyed this session. I hope you enjoyed too. Thank you. Have a good night.
Yes,
Okay.
thank
Thanks,
you,
Ben.
Thank you.
Bye.
Thank you. Thank you. Thank you. Bye. Bye.